Hello, chemistry students. Professor Sean McMahon here. So for today's lecture, we're going to cover chapter 3, which focuses on energy and matter. The first portion of chapter 3, the focus is more of general concepts, definitions, focusing on what matter is, how we can categorize it and classify it. This is a really good segue from the previous chapter that we covered, chapters 1 and 2, chapter 1 being the scientific method, which is basically following, again, that acronym OHEC: observations, hypothesis, experimentation, and conclusions. Chapter 2 then went with the kind of the experimentation portion of the scientific method, where we had to take measurements, and we focused on quantitative data because chemistry is a physical science. And that's when we went into, significant figures, how to determine them based on the precision of our instruments, whether it be a mass measurement, volumetric, length. We also talked about the metric system versus the English system. We talked about conversions. We discussed how we can use the conversion factor method to solve problems. And then at the end of our calculations, to use those significant figure rules and our units to give our final answer. So again, chapter 3 is a perfect segue. We're going to go straight into the classification of matter. Typically, students like this first topic. It's pretty straightforward. And like I said, it's more conceptual. The later part of the chapter, when we get into energy, it's more math driven and calculation based, where we'll be using a formula and performing calculations. But let's just get started and go straight into the topics of matter. So like I said earlier, chemistry is a study of matter and its physical and chemical changes. So that's what this chapter is about: matter and the physical and chemical changes it undergoes and the energy associated with those changes. So everything around us is made of matter. But besides matter, there's energy traveling through the universe. And we'll learn that that energy is actually traveling in the form of electromagnetic radiation. Okay. So basically, matter is anything that's defined that occupies space and has mass. So there's a difference between mass and weight. Weight is basically based on a gravitational force. So what do I mean by that? My mass, this space that I occupy, never changes. Okay, so it doesn't matter if I'm here on Earth or if I'm in space. So we know that in space, I'm weightless. Why? I'm not close enough to a gravitational force that will pull down on me to give me a weight, but I still have the same mass. If I land on the moon, per se, and you've seen pictures of astronauts where they can jump really high, that's because they have less weight on the moon, because the moon is much smaller, so it has a less gravitational pull downward on them. In fact, you would weigh about 1/6 of the weight that you are here on Earth, based on the size of the moon. So matter, we have to understand that some of it's visible to the naked eye, but some of it's microscopic and invisible. Doesn't mean that it doesn't exist. We know that substances or matter can be living or non-living. We know that. So a lot of times in biology experimentation, there's what's called in vivo within living systems, or in vitro outside of living systems when you perform experimentation. So some of you might have that background from biology. So I always like to start, and I'm going to explain this graph, but this is basically, this diagram right here is how we categorize matter. So everything that takes up space is matter. Now there's two major components. There's what are referred to as pure substances and mixtures. So I like to talk about, you already know these differences, and then I'll go into further textbook definition, but this is a great diagram. So typically pure substances, right, they have a definite composition. Their formula doesn't change, okay? Mixtures, you can change their composition, and the components in a mixture are not chemically bound, like in the case of a compound, okay? So under pure substances, right, you have two types. You have elements and compounds. So when we think of the periodic table of elements, so the simplest of all pure substances is an element. Okay, so here's an example of copper bars. Okay, so we use the elemental symbol Cu for copper. It's from the Latin-derived cuprum. We use a lowercase s here to show that at room temperature, it's found as a solid. So if I refer to the element copper, let's say pure copper wiring, if I was to break down that element into its smallest repeating pattern, I would get a bunch of atoms. So basically, you can think of element as the plural, and the singular would be an atom. So a bunch of copper atoms together would make an element copper wire. So and pretty much elements, they can't be simplified. You can't make them you can't break them down any simpler. There are exceptions with nuclear decay, and we will get into that later. But for the most part, that is what they are. Then you have compounds. So compounds, okay, they're still a pure substance and they have repeating patterns, but now you have two or more elements combined, and they're combined, they're bound. So they have a fixed ratio. So their composition doesn't change. So in this example, we see sugar cubes. Now, I like showing this because this also shows kind of a molecular model of what sucrose looks like. But a lot of times when you get to organic chemistry or biology, you'll kind of see this, line formulas, right? So with the line formulas, a lot of times the lines are representing, every corner is representing kind of a carbon, and there's hydrogens, but you'll see this structure. But basically, if we look at the chemical formula, and we'll learn all this stuff as we progress through, but if you look at this chemical formula, what we notice is that the compound of sucrose has 12 carbon atoms, 22 hydrogen, and 11 oxygen bound together to this fixed structure. Okay, now we can break the structure. The structure can undergo combustion and change into simpler pure substances like elements, but this is a pure substance. When I say sucrose, it is this molecule, okay? Mixtures are a little bit different. So we'll start with an easier, obvious mixture. We'll talk about the heterogeneous. Hetero means different or not similar. You can think of it that way. And here's a classic example of oil and water. So the water underneath, which everybody pretty much knows is, H2O, and there's an L, a lowercase l, to show that at room temperature, you typically find water in a liquid state. So water is polar, and you have oil, which is nonpolar, which means they have different characteristics. They don't mix very well because they prefer to be by themselves. So as a result, you get what's called a heterogeneous mixture. So we can clearly see that there's a layer difference between the oil and water. And you see in between them, there's like this interface that keeps them separated because they don't want to mix. This is also why we see, with oil slicks and things like that, oil is on the top of water and it doesn't mix. The other reason why it's on top, it's less dense. So if it was more dense, it would sink in the water. In this case, it is less dense. Homogeneous mixtures, you can think homo, meaning the same or similar, is where you have a uniform mixture and things are spread out evenly. Okay, so here's an example of tea. So the difference with mixtures is you don't have chemically bound components together. So for example, we do have water, which is a compound, just like this sucrose. We have sucrose, which is a compound, but they're not chemically bound, they're separate. And I can actually have them in different concentrations. There's not a fixed ratio. Like sucrose is always C12H22O11. But in my iced tea or my tea, I could have 5% sucrose in there, or I could add more sucrose. And because it doesn't bind to anything, I could just keep adding and increase the concentration of this sucrose to maybe 10%. And then Here's another example of a model. In this case, it's caffeine. So I wanted to show you, what the caffeine is. And when you're looking at these models, the other thing I wanted to kind of share with you is the black balls typically are the carbons, the white balls in these models are hydrogens, the red ones are oxygen, and the blue ones are nitrogen. So I wanted to show you how caffeine had a couple of nitrogen, and there's the chemical formula. Again, molecular structural models, chemical formulas, don't worry about it. I'm just trying to introduce it because you've probably seen it, and we're trying to categorize it with matter itself. So pure substances, right, versus mixtures. So again, a pure substance is composed of only one type of atom or molecule. So I said atom was a singular of an element. Molecule is the singular of a compound, right? So earlier I had wrote H2O. H2O is a compound. I could have pure water. I could purify water, and it would just be a bunch of water molecules together. So the molecule is a singular to the plural of a compound. So pure substances, whether it be water or an element like copper, has a fixed and constant composition. So that's what we saw with the copper, right? A mixture, again, it's composed of two or more different types of elements or compounds. It could be more than, one type, and combined in different proportions. So the substances can be mixed, and they're not chemically combined. They're not bound to each other. So again, that reference of adding more sugar to the tea. A composition that is not constant. So I could have 10% sugar, 5% sugar in my tea. I can change that concentration. Same with the salt solution. And the other thing about a mixture is I can actually separate it by physical means. So I'll get more into that later when we talk about physical and chemical changes, but I can separate them by physical methods. So what do I mean by that? Well, I'll get to that in a moment. Let's focus more on the pure substances, elements and compounds, and their singular atoms and molecules. So atoms are the particles that are the building blocks of all matter. So in many cases, the atoms are going to bind together to form these molecules, like in the case of H2O. Molecules are two or more atoms joined in a certain shape. So here's an example. Let's say I had an aluminum can. If I broke it down to the microscopic level, I would just see a bunch of aluminum atoms. So how would I write for that pure substance? So aluminum is an element. How would I write the chemical symbol? Well, if the element, the singular is just one aluminum atom, I would just do aluminum, and I would write S because it's a solid. I would just write the elemental symbol, and you can see this on the periodic table, Al, because this is showing that this is the consistent fixed ratio if I break it to its smaller part. So rubbing alcohol, right? If I had pure rubbing alcohol, it would be, and it is C3H, let's see, it's usually H, I gotta draw it. H7OH. So the reason why it's H7OH, this is isopropyl alcohol. There's an alcohol group in the center. That's why it's called isopropyl, like an isosceles triangle. And there are my hydrogens. So I have a total of 8 hydrogens, okay? But basically I have 3 here, 3 here, 1 there, and then 1 in the alcohol group. A lot of times what you see is you'll see this written out as CH3, CHOH, CH3. If I was to draw this a little more accurately, you get the carbon and you kind of get this bent shape, and you would see it's like an isosceles triangle because you have CH3s on both sides. Now, you don't have to worry about that right now, but as time progresses, you'll see that. The other thing is this rubbing alcohol. If it was pure, which typically it's not, but if it was pure, it would just be this pattern and this formula, the C3H7 repeating, OH. So elements, a pure substance that can't be broken down. Here's an example, helium atoms, just a bunch of helium. All known elements are listed on the periodic table. So helium, He, if you look on the periodic table, it has a number 2 by it. That 2 is called the atomic number. That's how we identify it based on the number of protons. Compounds, so water. You could have 2 or more elements. In this case, we have hydrogen and oxygen, and we write a fixed ratio of H2O. So here is the molecule, and we see that the oxygen's in the middle, and that's the red, and then the hydrogens are white, and they're right there. Compounds are more common than pure elements. Again, compounds are still a pure substance because they have this fixed ratio. Water is always H2O, and they're more common because elements tend to like to arrange themselves to help stabilize, and most of them are seeking to be stable. Most elements are reactive, and they combine with other, again, to form compounds to become more stable. We'll learn more about that when we talk about atomic structure. So here's an example of elements combining to form a compound. So I could have sodium. So sodium is a metal, and you can see this metal here. It's written Na and then a lowercase s because at room temperature, sodium, the metal, is a solid. Because it's an element and the singular is just an atom of sodium, we write Na. Chlorine is a gas. Now, chlorine is a unique element. So we notice that there's a 2 there. That's because it's one of the 7 diatomics. There are some elements that come in a diatomic form. So example, some of these elements bind to itself. We still consider this an element because it's only one type of atom. So because it's just chlorine, even though there's 2, we still call it an element, okay? So we have chlorine gas, it's a diatomic, we find it as Cl2, the G is for gas. When we put these together, they undergo a chemical change and they form table salt, sodium chloride. So what happens is these elements combine through a reaction and form a compound. Now the compound salt is still a pure substance because it has a fixed ratio of 1:1, sodium chloride, and it's a solid at room temperature. The one thing that this reaction, because this is how we write out reactions, we'll learn more about this later, we're basically writing out a chemical transformation or a chemical change, a chemical reaction, is we would have to balance on both sides. That'll be next lecture when we discuss energy changes and chemical changes, is that we have to have the same number of sodium and chlorine on both sides. So because we have 2 chlorine here and only 1 here, I have to put a coefficient of 2. And now I have 2 sodium, so I have to put a 2 there. Again, this is later down, but this is just to introduce you to concepts that are coming in the future. Going back to classifying matter, again, we had, pure substances, which are basically your elements, singular atoms. Compounds, the singular are molecules. All of them have fixed ratios. Now we go to mixtures. So mostly what we see are mixtures. So when we look at all the matter in the universe, most of it is a mixture. So what are some examples? Well, we could have the heterogeneous, which are varied in composition, and we could have the homogeneous, which is uniform. So in this example, air, right? So if we talk about air, if I look in my room, there's air, and it's a mixture. It has nitrogen, which is another diatomic. It has oxygen, and it has other trace gases like CO2 and water. But when you look at the air in your room, it's not like you can see the different molecules. They're invisible, but you don't see that there's a layer difference. It's uniform. It's distributed evenly based on diffusion. So the particles mix thoroughly and uniformly. So that would be considered a homogeneous mixture. Now, one might argue if I see smog, that would be an example of a heterogeneous mixture, but we're going to assume we have clean air, okay? Same with seawater. It's got salt, and here I show that the ions in the salt separate and they're surrounded by the water. So I could have a really concentrated salt solution or a less concentrated. And again, students say, how could you say that the ocean is homogeneous when there's seaweed and things like that? So even though we want you to think of it as being homogeneous because it's uniform if I poured it in a cup and it wasn't clouded with sand and things like that. But if there was sand in it, the sand would settle and that would be a distinct layer difference. So then that would be an example of heterogeneous. But the best way to do it is let's test where we are. So with examples A, B, C, and D, let us classify them as either a pure substance in a mixture. If they're a pure substance, are they an element or a compound? If they're a mixture, is it homogeneous or heterogeneous? So you can pause the video now, work on it on your worksheet, and then unpause it, and we'll go through the answers. So seawater, again, we're going to assume it's a homogeneous mixture because it's uniform, because the sodium chloride deionizes and dissociates and spreads evenly throughout. Sugar. So remember I gave you the formula for sugar, C12H22O11. So this is an example. If I had pure sugar, be a pure substance and it's a compound. Why is it a compound? Because it's more than one type of element. There's carbon, hydrogen, and oxygen that are bound together to make sugar. Why is it considered pure if there's more than one type of element? Because it has this fixed ratio. Mercury in a thermometer, that's a pure substance and it's an element. If you look on the periodic table, you can find the elemental symbol mercury, okay? Mercury is kind of unique. It's one of only two elements that are liquid at room temperature, and it's unusual because it's a metal and it's found as a liquid. So that's typically pretty unusual. So chicken noodle soup, is that pure substance? Like, is there a fixed ratio of the noodles versus the pieces of chicken, or is it a mixture? Well, it's a mixture. Why is it heterogeneous? Well, you can separate things. I always like using the example of trail mix. You know, it's really easy to pick the M&Ms out of your trail mix, right? So there may not be even distribution of the M&Ms. You might not always have the same amount, but you could easily pick them out, right? Because you can see them and there's not a fixed ratio. So on that topic, when we talk about mixtures, one of the things that we do in lab is when we have mixtures, we want to separate them into their pure substances, their pure components. That's actually really common. So one example of separating liquid to liquid mixtures, so where both components are liquid state, is distillation. So let's say I had a water and alcohol mixture. I can take advantage that the water actually has a higher boiling point than the alcohol, the ethanol, and I can boil off the ethanol first and then condense it and catch it based on its boiling point differences. So we're using differences in the pure substances' physical properties to separate it. Another example is I might have, instead of a homogeneous mixture, like two liquids mixed, maybe I have a little bit of a suspension. I have some solid. Earlier I had said sand, but it could be a different type of solid in a liquid solvent. Well, how could I separate that? I can use filter paper and use gravity filtration to separate it. And then the filtrate will come through. So that would be the liquid portion and the solid would remain. This would be an example of a heterogeneous mixture. You can think of this as when you have the coffee grinds in the filter, right? And then you run the water through it. The filtrate that comes out extracts the caffeine and other portions of the coffee, so you get the coffee filtrate, but the solid residue remains separated based on its components. So in lab, a lot of times we'll take two clear solutions, combine them, and we'll get a really pretty color. That color is referred to as a precipitate. Really, this is a solid, okay? And the solid might be suspended, but I can use what's called centrifugation. It's basically a rotor where I could put the test tubes opposite of each other and spin it really fast, and the force will cause the solid to go to the very bottom. If that's the case, it's really easier. It's easy to separate it because that force will cause all the solid to form a little pellet at the bottom of a test tube. That's typically referred to as your precipitate. And then the fluid above that could easily be separated because now this precipitate is stuck to the test tube, and this could be poured off into another container. This liquid above is called the supernatant, and you can separate it by what's referred to as decanting. That's another technique. Now, if you don't want to spin it or you don't have a centrifuge available, right? How could you separate this solid? Now, the reason why it's solute is it's not soluble. What that means is it doesn't mix, right? It has different properties. So this insoluble solid, right, can be separated from the remainder of the liquid. So I could separate the solid. How? What I said before, I could use filtration. So the solid's big enough, when I pour this solution, or actually this is a mixture, it's a heterogeneous mixture, and it would be a suspension. I can pour this suspension through the filter paper, and because the solid's big enough, it will stay trapped in the filter paper, and then the liquid will pour through. So that is a separation technique for mixtures. It's harder when they're evenly mixed, like the homogeneous mixture that I talked about, like with the water and the alcohol. And that's why I have to do the distillation technique. And that is based on the more volatile liquid will vaporize faster. So I'm throwing a lot of terms and writing things. You're not expected to know everything. I'm using things that we're going to see consistently all semester long. Okay, so volatile means it vaporizes faster. It's volatile. You can think of it as violently, escaping, or it boils violently. So it goes from a liquid state to a gaseous state easily. An example would be gasoline. And on a hot day, if you ever put gas in your car and a drop falls on the asphalt, it'll appear to dry up and go away really fast. Why? Because it evaporates rapidly, because it has a low boiling point. The lower the boiling point, the easier it is to vaporize, or the more volatile it is. Water has a really high boiling point. So when you do distillation, the water remains behind while you can separate the more volatile liquid and catch it in what's called the receiving container. So the more volatile liquid, once it boils off, it's in the vapor state. Well, if you have this little condenser, it's basically a glass elbow, and you force, because as you drive the gas up, if there's a stopper there, the gas is going to go in this direction. Now it's a gas. Well, if you put a jacket around this tube and flush cold water through, it'll cause the vapor, now it's getting colder, to recondense into a liquid form, and that's how we can catch it. So what we're really doing is we're looking at elements, right? We're looking at pure substances, which are elements and molecules. We're looking at mixtures, which are some combination of these, but not in fixed ratios. And then we're saying, okay, with mixtures, we can separate them. Well, how can we separate them? It really depends. Does the mixture have a solid and a liquid, or is it two liquids? So now that we've talked about how we can separate them, I wrote a little bit about how we write them in elemental symbol form or molecular formula. Remember, for copper, I wrote the S. For water, the S stands for solid. I wrote an L because it's a liquid. For the chlorine, one of the diatomics, I wrote a little G because it's a gas. Now I can talk about how we find these in different states of matter. So what are the states of matter? Solid, liquid, and gas. So in a solid, basically, it's based on how close the particles are aligned. When I say particles, the atoms or the molecules or the ions. So with solids, the particles are really close to one another. So as a result, they have a definite shape. That means it's a fixed shape. So like your table, it has a definite shape. It doesn't change its shape. Why? It's a solid. The particles are really close. It has a fixed volume, a definite volume. The volume doesn't change. It has a rigid pattern. If we go at the microscopic level, it has a pattern to the solid. Now, a lot of people, when they look at solids, they don't think, okay, these aren't moving because it's, you know, at a macroscopic level, it's not moving to the naked eye. But in actuality, even solids have some movement in what's referred to as vibrational movement because the atoms can vibrate within their fixed pattern. Again, a lot of these concepts I'm throwing out, I'm introducing, but we'll come full circle and learn about them a little bit more later as well. There's two types of solids, the crystalline solid and the amorphous. Crystalline is a regular repeating pattern. Amorphous is not as uniform. So salt, NaCl, has a fixed pattern, okay? So you can see the chloride ions and the sodium ions in a repeating 1-to-1 ratio. That's why we write it as sodium chloride, and it's a solid. Why? For every sodium, there's one chloride. Now, sodium chloride is a little bit different than what I had earlier with water, okay? Water actually comes in a molecule, right? So here's my water molecule. If I have a bunch of water molecules, that's called a compound. So a glass of pure water is a compound, and all it is a bunch of water molecules. This salt crystal, it really doesn't have molecules. That's because it's ionic, and we'll get into that a little bit later too. It actually has what's referred to as a formula unit ratio. What this is actually telling me is the ratio of sodium to chloride. Just like in the molecule, there's one oxygen to 2 hydrogen, but there's more than one water molecule in a compound. So with sodium chloride, the ratio is 1-to-1, that's fixed, but there's more than one sodium and chloride ion. So this is a repeating solid structure, and this is actually known as a crystal structure or a lattice crystal structure. Amorphous solids, they're a little more flexible. So I tell students, think about rubber, right? Or like a soft plastic, right? With a rubber band, you can stretch it. So it doesn't have quite as fixed the shape. It does have a shape. And I mean, if you pull it too much, it'll break because it has some shape, but it has a little bit more flexibility because it's not as tight and uniform as a crystalline solid. What about liquids? So liquid, right? They're closely packed, but they're not as close as solids. So as a result, even though they're close to each other, there's a little bit more mobility in the motion. They can freely move past each other. I call it kind of like a slipping and sliding motion. So as a result, they can flow, right? You could pour a liquid. So they have a definite volume, but not a definite shape. So I know I keep using water, but it's a really common liquid and a pure substance. If I poured water, I could pour a 12 fluid ounce bottle in a glass. I could keep it in the bottle it came. I could pour it in a bowl, so it will change its shape, but it'll have a fixed volume. It has a fixed volume because the particles are relatively close, but because they're a little further away than the solids, they can kind of slip and slide, and that's why they take the shape of their container. Same shape as their container. So that mobility is called freedom of, it's a degree of freedom. It's a freedom of motion. And that allows us to pour. Now gases, they're extremely far apart. They're not closely interacting at all. They don't, you can think of it as stickiness. Solids stick because they're really attracted to each other. That's why you got a fixed shape. Liquids stick, but they're not as attracted as solids, so that's why they can kind of slip and slide and keep their volume. Gases, there's no stickiness. The particles are far apart from each other and they don't stick together, so they fill up their container because the majority of space they occupy is empty space. Now they spread out evenly, but they do not have a definite shape or a definite volume. So they don't have a definite volume. That's why gases can be compressed. You can change their volume and their shape. Why? Well, the majority of it is empty space. They take the same shape and volume as their container. The particles are far apart. And the other thing, I didn't really mention it, is we had talked about how solids doesn't look like they're moving at a macro level, but at a micro level, they're close to each other and they're stuck because they're sticky in this fixed lattice structure. But there's a little bit, they're vibrating, right? There's some thermal energy. Liquids, there's a little more movement, right? They're slipping and sliding, so there's a little more motion. Gas particles, because there's no stickiness, they're just flying in all directions. They're flying all over the place. So they're fast. So that's a little discussion on the different states of matter. So now we can talk about different properties of matter, whether it's a solid, liquid, or gas, is kind of dependent on physical properties, but we'll also talk about chemical properties as well. So a physical property is one that a substance displays without changing its composition. So there's no change in the formula. So for example, aluminum, right? It's one type of atom. So I have just the elemental symbol aluminum because that's the repeating pattern, a singular atom of aluminum. There's an S because it's a solid. I can take an aluminum can, right? And because it's a metal, it's malleable, right? And I can crush it. So I can change its shape, right? That's a physical change, but it's still aluminum. That's because a physical property of aluminum is that it's malleable. I can bend its shape. Metals are malleable, right? I can hammer them and make them swords, right? They're ductile. I can draw them out and make wires, like copper wires. Chemical properties are where there's actually going to be a change in composition. Really, a chemical change is a reaction, and that's what we study in chemistry. Matter and the reactions they undergo and the energy that's, combined during that reaction. So whether energy is released during the reaction or absorbed for the reaction to take place. So a chemical property, you may have seen this, a lot of the hazard signs where you'll see like, a circle and there's a line going through and you see, flames. That's because it's combustible or flammable, right? Or you'll see the hand and there's like a drop showing that the hand's disintegrating because it's corrosive. Those are chemical properties. That means those substances can react with things very quickly. So you need to be careful. okay? Because if it reacts quickly, there's going to be a change, and it might be a change that's not favorable. So what are physical properties? Think of your physical senses, odor, color, but really what I think is really important are the melting point. So when does it go from a solid to a liquid? That's your melting point. And then your boiling point is when it goes from a liquid to a gas. That's your boiling point. The other physical property that I think is very important, we already talked about, is density. And you may remember density is mass over volume, DMV. If you know a pure substance melting point, boiling point, and density, then you can narrow down what it is very easily of all the possibilities just by knowing those three physical properties: melting point, boiling point, and density. Now, again, there's other ones like solubility. Does it dissolve in water? Things like that. But those three are very important. At the boiling point, water is converted to steam. But steam, right? The reason why this is a physical property is there's no change in composition, right? So I have liquid water, H2O. If I heat it up, it escapes, right, into a vapor, a gas, because I'm boiling it, but that gas is still water. It's still H2O. There hasn't been a chemical change. That's because boiling is a physical property. It's not breaking the bonds in the H2O molecule. So it's not breaking these bonds. All it's doing is separating the attractive force between the water molecules. So you're separating it. It's called intermolecular force, the attraction between the molecules, but not breaking the bonds within. Chemical properties is where you actually change its composition. So if you leave iron out, especially if there's a lot of moisture or heat, it starts to what's called oxidize. What does that mean? It starts to combine with iron oxide, and that, or iron 3 oxide, and that is basically rust. So it starts to change. It starts to absorb or combine with the oxygen. So with that being said, let's see, is it a physical or a chemical property with these 4 examples? So you can pause the video if you have the sheets and fill it in, or when you're ready, we can just go right through it and you can unpause. So hydrogen gas being explosive, is that a physical or a chemical property? So what might help is an explosion a change in composition? Yes, it is. So that's a chemical property. Hydrogen's explosive. It can react and explode and release a great amount of energy. Hydrogen bomb, right? Silver has a shiny appearance, okay? So remember, if we're talking about something with the physical senses, right? It's texture, touch, it's color, sight, right? If it's a solid, liquid, or a gas, because that's a state, that's a physical property. Dry ice sublimes. You may have gone to Baskin Robbins and maybe got an ice cream cake and they give you a piece of dry ice. Dry ice is basically solid CO2. And what it does in our 1 atmosphere, right? Atmospheric pressure is it goes from a solid directly to a gas. So it goes straight into a vapor phase. That's called sublime. Okay, so if I go from a solid to a gas, did I actually change my composition, or am I still CO2? Because that's what dry ice is. Still CO2, it's just changing its state of matter. So that's a physical property. If copper over time, sometimes this is referred to as patina. This is what happened to the Statue of Liberty, by the way. If copper turns green when exposed to air, we call that oxidizing or rusting. That's a chemical change. It's absorbed the oxygen and now there's a change in color because it's no longer copper, right? If it was copper, it would stay that pretty brown color. But once it oxidizes, it changes, right? So like a bluish green aqua color. That's your copper oxide. Could be copper 1 or copper 2 oxide. We'll talk about that too. So we talked about physical properties. We use our senses. We talk about chemical properties. Is there an actual change in composition when something occurs? So how's this all going to happen? How are we going to identify these things? Well, they're usually, we can identify the property as being physical or chemical by observing some type of change, right? So how do we talk about, boiling point being a physical property? Well, we showed a pot of water in liquid state. I put energy in it. I separate the molecules. It becomes a gas, but it's still water. So that's a physical change. Okay, so in that case, there's a change in appearance because I went from liquid to gas, but it's still water. So it's only a physical change. And that can be tricky. Chemical change, matter does change. And that's where you would also see, possibly a change in state. In this example, it's not because iron is a solid. And then when it rusts, iron, 3 oxide remains a solid, but you can have an actual change in state of matter. So you can go from a liquid to a solid sometimes. But with all chemical changes, basically when you think of a chemical change, you're thinking a chemical reaction. And I cut reaction as just short script RXN. So typically how it works is the reactants are your starting materials. It's what you start with. And then the products are what you end with because you produce those. So earlier we had written out, sodium as a solid plus Cl2, chlorine as a gas, gives me the salt sodium chloride, which is a solid. But to balance this, I had to do 2, right? Now, in this example, I have iron, which is a solid, and oxygen, which is another diatomic, O2, and I form iron 3 oxide. So that formula, we'll get into this later. And it's got to have a S to show that this is solid. Now, to balance this, I have to have the correct number on each side. There's 2 oxygen here. There's 3 oxygen on this side. So 2, 3, they're not the same number. So I need to multiply them to get a common multiple. Well, both 2 and 3 go into 6. So I multiply 2 by what number to get 6? 3. I need to multiply what number to get 3 to 6? 2. Now I don't change this number here because this is the ratio in the formula. It's called the subscript. And when I look, I have now 2 times 2 iron. I put a 4. This is way ahead, by the way. This is like chapter 6. We're only in chapter 3, but I'm giving you a little taste of what's to come and how our discussion of chemical change, really what we're doing is it's a reaction. And I could use words. I could say iron atoms oxidize in the presence of oxygen to produce iron 3 oxide, or I could use chemical formulas, which are really symbols of the reaction, and then use the coefficients, those are the numbers in front of the formulas, to make sure that I have the right number of each type of atom. So it's a balanced equation, because in next lecture, we'll learn that you can't create or destroy matter. You can only move it around and combine it or separate it, right? We can't create or destroy matter. All we can do is shuffle it around. We can change it and transform it, but we can't, create it. That'd be pretty awesome, but we can't. So physical change is a change where the chemical composition of the substance is not changed. Here are some examples, right? So I might have a change of state. I'm going, right? I'm changed, but it's still a physical. When I boil water, I freeze water, right? Going from a liquid to a solid, it's still water. I could have a change of appearance, right? Dissolve sugar in water. So it might, you know, be a little cloudy, but it's still sugar and water. And you know, because when you taste it, it tastes sweet. So it maintained its, you know, chemical properties, right? There's no chemical composition change, and you know that, right? So when I dissolve salt in water, that's a physical change. I separate the ions and separate them. It's not a chemical change because when I drink the water, it tastes salty. It still tastes like salt. I can change shape, right? Like I said, hammer things, still a metal. And I can change size, right? I can take a piece of paper and cut it, still paper, right? Chemical changes is you change its composition. So that piece of paper, instead of ripping it, if I light it and it changes, now I know it's no longer paper, right? The composition of the substance changes during the chemical change. So the tarnishing of silver, basically that's also called patina. You could also say rust almost, but tarnishing of silver reacts with air to give a black grainy coating. Burning of wood, it converts it to water vapor and CO2 and energy. Caramelizing sugar. A lot of times people, when they cook, they caramelize, brings the sugar out and makes things sweeter, like with onion, caramelized, you know, grilled onions. Formation of rust. So here we're seeing chemical changes. And as a result, once there's a chemical change, there's a change in the properties of the newer substance, okay? So now that we've talked about, all right, here's matter. We got pure substances that have fixed ratios, right? And you can't really break them down any further, right? Unless there's a reaction. And then you have mixtures which don't have a fixed ratio. They're not chemically bound. And you can separate them using filters and distillation. Then we talked about properties. And now we're going to talk about what is evidence of a chemical reaction or change. So you can say, all right, that's chemical property. So if I take two substances, combine them, and without heating it up to vaporize it, because the heat will boil it. But if I just take two, let's say liquids at room temperature and combine them and bubbles start forming, that means there's been a change. I produced a gas, okay? It's not a physical, you know, it's a physical change as well, but it's not because of physical, I'm actually chemically changing it. Like if I add Alka-Seltzer and it starts fizzing, that is a chemical change, okay? Any light or heat released or absorbed is a chemical change, right? So when you burn wood, right? I'm not burning wood in a fireplace because I want a bunch of ash, right, and soot. I'm burning it because when there's that chemical change, it's also releasing a bunch of heat to keep my house warm, right? We don't burn gas because we want to, you know, increase CO2 emissions. We burn gasoline because we need the energy to move our vehicles and machinery to do things that make our lives easier, right? I mean, try to travel 44 miles with a trunk full of stuff in your car by pushing it. You know, I know gas is really expensive right now, but, you know, gosh, it's almost like, it's like $5. But, you know, that $5 seems to make more sense where if I was to say to you, all right, load your car up and push it for 20 miles to save $5. You start realizing that that's why we burn gas. It does a lot of work for us. Formation of a precipitate. So if I take two clear liquids and I combine them and I get this color change, a lot of times that color change is actually a precipitate. Precipitate, I actually denote this as PPT. That's shorthand. PPT just means precipitate is a solid. This is just a solid. And right now, it's fluffy and suspended. But remember, I can spin it in a centrifuge and have it pellet, or I can filter it and catch it in a filter paper and then put it in an oven or just let it air dry, and then I'll have a solid that I can weigh. Or again, if there's a permanent color change, that's evidence of a reaction. So all of these are evidence that, okay, I changed some composition of my matter. This is a chemical change, and this is letting me know that. You just need to be careful, because sometimes a chemical change will also have a physical change, like in the example of the bubble formation or the solid formation, but it's also a chemical change where you could boil something, so there's a physical change, liquid to gas, but there's not a chemical change because that boiling, you still have water. I like using this example. I know it's kind of goofy, but here's an old school lighter. You have, your butane in the lighter. C4H10 is butane. And it's under pressure. That's why it's a liquid state, but it easily vaporizes. Why does it easily vaporize? It's volatile, right? That means it has a low boiling point. So if I push down on this little lever, that releases an, whoops, sorry about that. That releases an opening in this lighter, and then the butane can escape and vaporize really easily. But it's still butane. That's only a physical change. I'm going from a liquid state to a gas state. But if I ignite it with a spark, so I need something to initiate the burning, right? So the wood in the fireplace doesn't spontaneously combust, right? I gotta give it a little bit of energy to get it going. So if I give a little spark, now I can burn the liquid butane, and I can now produce, and you see it here, CO2, the middle one, that's black, the ball is your carbon, and then on the two red are your oxygens, and H2O. Again, red is oxygen, white is hydrogen, and black is your carbon. So you'll see in a lot of molecular models, there's a ton of black and then a ton of white and red, because most of your organics, right, organic compounds, biological systems have carbon, hydrogen, and oxygen. Let's see how you're doing. And this will be it for the first lecture of chapter 3, where we were primarily talking about matter, how to categorize it, and how to identify physical and chemical properties. And to make it easy, how do we do that? We observe physical and chemical changes. So copper metal forming a blue solution when dropped in nitric acid. So you can just think, I take a piece of copper, I throw it in nitric acid, and now a blue color happens. Is that color change evidence of something? It's chemical reaction, chemical change. There's a change in composition. A train flattening a penny. I used to do stuff like this. You take a coin, you put it on the railroad tracks, obviously you don't stay there. You run out of the way, the train goes by, you go back, and now it's flat. Well, the penny is still the penny. I didn't change its composition, I just changed its shape. So what is that? Physical change. Still has the same amount of, unless some of the train scraped it off, but it still has the same components. It might still have the same mass, right? Usually when it's a physical change, it has the same mass if you contain everything. A match igniting a firework. Firework, is there a release of heat and light? Yes, so that's evidence of a chemical reaction, a chemical change. Ice melting into liquid water. So I put an ice cube on the table, it starts to slowly melt. What is that? I know there's a state change, but is it physical or chemical? It's merely physical. It's still H2O. There was not a change. So I want to thank you. That, again, is for the first part of chapter 3, our discussion of matter and its physical and chemical changes. We will continue with chapter 3's discussion, and we will, on the next lecture, discuss the different forms of energy, how we can transform them, what are units of measurements of energy, and some basic definitions. And then that will be followed by energy calculations. So I want to thank you for listening and staying tuned, and let me know if you have any questions. Thanks so much.